In this video, we're going to be discussing how stars form. Our story is going to start with a spherical cloud. It'll become spherical in a moment. There we go. A spherical cloud of hydrogen gas in the vacuum of space collapsing under its own gravity. We're going to talk about what that means, and we're only going to be using Newtonian gravity, so there are really no prerequisites to this video other than a basic knowledge of Newtonian mechanics. So let's get started by building up some intuition. Imagine that we have two particles, one with a large mass m and another with a small mass m. If I let them interact only gravitationally and I let them go, where would they meet? It would be somewhere around here, right? That point has a special name called the center of mass. It is never going to change through gravitational interactions alone, and the particles are going to meet at that point. So if I let them go, they should evolve to something like this. This is the center of mass, the big one comes here, small one comes here. So let's say this is a distance r1 here, and this is a distance r2 for the smaller mass. So if we take seriously the fact that these are only interacting through gravity, then the question is, when do they stop? Would they ever stop? The answer is no. They should pass right through each other, so if this interaction continued, they would switch places like this, and then the large mass would keep moving over here, a distance r1, and then the smaller one would keep moving over here, the distance r2. So it would be exactly the symmetric version of what we started with. That's when they would come to a stop, and then they would start moving back the other way to their initial positions. So if we looked at the two of them individually, the large mass would just go r1 over here from the center of mass, and then r1 over here again, and then back. They're acting like harmonic oscillators. The small mass like this, distance r2. The point that I'm trying to make here is, if we look at Newton's law of gravity, we can write down a force of gravitation like this. It is only scaled by this 1 over r squared on the bottom here. But everything that has mass is always attracting everything else that has mass. There are no massless particles in Newtonian mechanics, so that means everything in the universe is attracting everything else in the universe. So through only gravity, we have things falling. Falling is the most natural thing that an object can do. Where things actually get interesting is when they stop. There will have to be other forces in play to make them stop. So to start thinking about that, let's go ahead and draw another spherical gas cloud here. Yellow, that's obviously the color of a star. And just imagine that there are countless particles inside this sphere and that they are all starting to now collapse under their own gravity. So it's just like what we had with two particles. They would collapse towards the center of mass, which is in the middle over here. And then if nothing stopped them, they would pass right through each other, and then they would mirror their first positions. So this particle would just come here, and then they would collapse back, acting like harmonic oscillators as we have seen. So this would just be a sphere that collapses and then grows back to its own size except mirrored, and then it collapses again and returns to its initial state. Okay, so to stop that from happening, we already have to introduce another force, electromagnetism. What does that do? Well, it turns collisions on. So now the particles are interacting with each other through their electric charge. Which electric charge? Well, we said that we have atoms of hydrogen in this gas cloud. So a hydrogen atom just has a single proton in its nucleus and then an electron in orbit around it. So it might look something like this, just make it somewhat fuzzy to draw a bad picture of quantum mechanics here. The point is, the nucleus is very small here in the center. I think it's 10 to the minus 3. It's 1,000 times smaller than that first electron's orbital. So it is their electrons that actually interact first when you put these two atoms close together. There's actually minus negative charge much closer to the other atom than there is positive charge here. Okay then, that is the next chapter in our story. We need to now figure out at which point does this gravitational collapse stop. So let's look at a region around the center of mass here. We have more and more particles trying to come into here through the gravitational collapse. But as they do, as they start to get cramped up in here, now there are more and more particles being put into this little volume. And so with a very simple picture here, we can just imagine that there is charge, there's electric charge starting to emerge here. There are more and more collisions happening inside this small volume that whenever a new particle comes in, there are now crazy particles going around in here very ferociously at very high energies. So once another one approaches, one of them just smacks it away and it cannot get to the center. This is what we call pressure. As you put more and more particles into a smaller volume and do it with acceleration coming in from here, again that is just the gravitational force doing work on these particles. They are all accelerating towards the center and then they are starting to collide. So this is when our antagonist is starting to emerge here. It is strengthening. The pressure in the center is increasing. And it is proportional to the number of particles that are in here and the temperature, and it is inversely proportional to the volume. You know this from the ideal gas law, of course. But intuitively, we are squeezing more and more particles into a smaller volume and their energies of collision is starting to increase. That is what pressure is. And mathematically, of course, we show it with a force that is affecting an area. So you divide up a force into an area. And the area here would be the surface of a sphere. That's 4 pi r squared. That's going to come in handy in a second here. This concept that we're building up here, it has a name. What is going to stop the gravitational collapse is called hydrostatic equilibrium. And right now, we're going to try to formulate it. So it's time to do some math. To get started, let's reimagine our star, or well, to soon become a star here. And let's imagine that it has layers. It's made up of these many thin shells of infinitesimal mass. Just imagine more and more of these shells eventually becoming the sphere. It's very much like an onion. Well, for the gravitational collapse, which just pulls all of these shells uniformly towards the center of mass, for it to stop, we need the net force on each of these shells to become 0. That means we need to first calculate the gravitational force that is affecting each of these shells. Okay, to do that, we can just imagine a little particle here being pulled towards the center of mass. What would be the force on that? If you have taken electromagnetism before, you know that the electric field inside of a spherical shell is 0. And of course, this is not unique to the electric field. Both the Coulomb force and the gravitational force are inverse square laws. And they have really nice properties with spherical symmetry. Let's think about what that means. So if we take a spherical shell here, we put a particle, let's say, over here. And just imagine again that there are countless particles here building up this sphere, or in this case, circle. So we have our particle in the middle here, and we have these particles pulling on it with gravity. On this side, we have fewer particles, but they are closer to the particle that is being pulled on. But on this side, we have particles that are further away, but we have more of them. Even though I didn't draw them here, just imagine again that there are countless particles making this up. So which one of these effects is going to win? Well, it turns out that they are exactly equal. And of course, that is no coincidence. Gravitation and electromagnetism, the forces, they scale on spheres. If we write down the Coulomb force here, it is 1 over 4 pi epsilon 0, and then you have these charges, call them q and q prime, over r squared. This is usually how we write it down, but a more suggestive way to do it is to just put the 1 over epsilon 0 here, maybe put the q's here, and then we have 1 over 4 pi r squared. That is the surface of a sphere. There's no reason to put these apart. Geometrically, a simple way to think about this is to think about divergence. If we have arrows that are diverging away from a point in the middle here, if you draw a circle over here, you have what we might call a larger density of arrows, right? There is this much length between where all the vectors are passing through. But if we draw it over here, there's much more distance between each vector. This is how gravity and electromagnetism are scaled with distance. On the surface of a sphere, they disperse. And so it really shouldn't be a surprise that when we have a spherical system that looks this way, of course the force is going to balance out. It's exactly the same symmetry. So while we have the vectors of, let's say, these particles, let's just take this particle, its vectors are slowly dispersing, right? It looks something like this. But we also have the same exact sphere, and we're adding more particles to it. It exactly counteracts the dispersing of the vectors by adding more vectors. Okay, let's just get rid of all this now. And we are back up here. Now we can make a fresh start, armed with the knowledge that the force inside of a spherical shell is 0. So if I pick a particle at any point inside the sphere, this shell is going to have 0 effect on it. It's only going to be pulled by the shells that are in here. So now we can write down Newton's law using this knowledge. Let's just call the distance that this particle has to the center r. And let's call the mass of all of these shells in here added up mr. So all the masses up to the point r. And this is our little dm here. We can write that down there. And now we divide by r squared. And since we have used an infinitesimal mass, we get an infinitesimal force. All good so far. What else do we know? Well, we know that the inner pressure, so what is pushing against all of these shells from within, has to be equal to the force of gravitation at any point. So if I draw this little vector here, it should be such that the net force on this little dm adds up to 0. So we can write that down as this Fg, infinitesimal force, is equal to whatever the pressure is in there times the area that both of them are working on, right? We have to multiply the pressure by an area to turn it into a force so that we can write it equal to a force. So now how about this mr? How can we write that one down? We're going to assume that we have a constant density throughout the star, and I'm going to justify that assumption in a minute. Then we can multiply this by the volume. So 4 pi r cubed is the volume up to this radius over here. And that would give us the mass up to this radius. Now if you take this mass, this is the mass up to this r, and you add a tiny other shell of infinitesimal thickness and infinitesimal mass, dm here, you would get how much the mass has changed with an infinitesimal change in radius here. So this is dr. What I'm trying to say is if I go ahead and differentiate this, dm over dr, I would get 4 pi r squared rho. And then if we throw this to the other side and take a differential, dm 4 pi r squared rho dr. dm would be equal to this. So this would be the mass of this tiny little shell of tiny thickness that we have added here. That is what we had up here, the dm. Let me go ahead and copy that down here. And now we can just plug in what we have found to solve this equation. So by writing down this dm here, we get that dfg is equal to minus g mr 4 pi r squared rho dr over r squared. The r squareds do cancel, but let's just keep them for a second because we said that this, the force, is equal to a dp. And we know that this area is also 4 pi r squared, so it's better to cancel these out instead. Okay, so with that we have minus g mr, and the 4 pi r squareds are gone. We have rho over r squared dr is equal to dp. We can differentiate both sides by dr and get that dp over dr is minus g mr rho divided r squared. And this is what we were looking for. This is the hydrostatic equilibrium equation. And it is one of the fundamental equations that describe the structure of a star. Let's try to understand what it's saying. So first of all, the static here means that we have assumed that the accelerations are zero. Now, of course, in our collapsing star, we have all of these particles getting accelerated towards the center. So how can we say that the acceleration is zero? Well, the point is, when we have an equilibrium here, so we have the same force pushing away from the center, we expect the particles to eventually become static. And now we are deriving the condition for that to happen. So when this equilibrium happens, we do expect the particles to stop. What we are really neglecting here is a lot of fluid mechanics. Whenever things get hot in here, they tend to flow outside with these wonderful patterns that even give rise to magnetic fields and everything, but we're neglecting all that for now. So what's interesting about this equation is it doesn't say that the pressure is equal to something. It says that there is a pressure gradient. It says that the pressure is changing with radius, and it's changing in a negative way. So as you get away from the center, the pressure has to get smaller for there to be hydrostatic equilibrium. The pressure cannot be constant. And this is intuitively clear, because if we again draw another star and a center of mass here, and let me just take a slice out of here. If I were to look over here in this radius, for example, for this to become static, this little part over here, this tiny slice in this smaller circle, it has to hold up all of the mass that is up here. So if you're closer to the center, you have to hold up more weight. So there has to be more pressure in the center to counteract there being more particles trying to collapse in there under the force of gravity. And the hydrostatic equilibrium tells you exactly how much that pressure has to change to counteract gravity at each infinitesimal layer of the star. And with that, we can go back to that little promise that I've made that I would justify our assumption of a constant density here. Because of course, in this equation, the density has to be important. More density at a shell would mean that there is more pressure there. But the point is, we can just write down the r here after having assumed that it is constant when deriving this formula. And this assumption again works because of spherical symmetry. At first, I want to talk about what gravity does. So once you get a system that has a constant density everywhere and you let it collapse gravitationally, it collapses until there is hydrostatic equilibrium, right? That means that things either need to get hotter and hotter as you go towards the core, or things need to get denser and denser. What really happens is both. So what gravity does is it always changes the density from being constant to being more towards the center. So by assuming that the density is constant in the beginning of the interaction, we haven't done much because we know that gravity is going to make it denser for smaller r anyway. And then the spherical symmetry argument is the fact that when we have a shell, let me just take this one because I'm tired of drawing shells. if it has a certain density here, spherical symmetry tells you that the density on this side should be equal to the density on this side. So rho here is only going to depend on r. And that's why I can just put the r here, because we're already differentiating with respect to r, and we know that the pressure is going to change only dependent on r. So we have made a lot of progress. In fact, we're almost there. So we know that in order to stop gravitational collapse, let me just call that gravit-call for short, because why not? We have to stop it by reaching hydrostatic equilibrium. And for this to happen, the core needs to heat up, so heat plus, it has to contract, so volume minus, and it has to get denser, so density plus. The next question is, why are these things happening? Well, the gravitational collapse itself is accelerating particles, so heating them up, giving them more kinetic energy to collide with. It is collapsing, so the volume is getting smaller and more particles are going to the center of mass, so the density is increasing. So gravity is creating its own antagonist here. Now, if this is enough and hydrostatic equilibrium is reached by gravitational means alone, then a star does not form. Well, something forms, but it is not a star, because the requirement to become a star is to do fusion in the core. If that does not happen, then this body will be called either a brown dwarf, or if it is smaller than that, it might just be a planet, it might be a moon, an asteroid, whatever it might be. So how do we get fusion? The next chapter in the story. Well, we need the hydrodynamic equilibrium to not happen. This happens through mass and through radius. There is a mathematical condition called Jeans' criterion that can predict whether a gas cloud is going to collapse into a star or not. And it does it through mass and how that mass is distributed. We're not going to get into that right now. Let's instead talk about how it actually happens. So the story so far is there is a gravitational collapse. This particular gas cloud is so massive that gravity cannot be stopped. It just keeps on collapsing. The core never has enough pressure to counteract gravity. Well, it keeps on collapsing. And that keeps on building up more pressure, which still is not enough. The core is not getting hot enough. It's not getting dense enough until it does. This is when the core gets so hot and so dense that quantum effects start taking over to start nuclear fusion. Let's talk about how that happens. So imagine that you have two magnets. They both have two poles. You take the north poles and start to squeeze them together. That's not the way the arrows go. There we go. They will try to push each other apart. As you get them closer and closer together, it's going to become more and more difficult to push them into each other. So if we were to plot a potential for this, we may imagine it looks something like this, right? So both of the particles have these positions here. You push them closer and closer together. It starts to take more and more energy to try to push them together. Now, if you have played with magnets, you may have seen before that if you push them close enough together, sometimes one of these magnets just tends to flip in your hand. You just cannot grip it that strongly, and the south pole comes here. And then you are at this situation where the poles are now reversed and you are just pushing them closer to each other as hard as you can. And this one just flipped in your hand, and now they're going to stick together very ferociously, sometimes just breaking the magnet, other times making a loud noise. This is what happens in nature. So this potential looks very much like this. and this just goes down here. So what we have up here, up to this point, is the Coulomb force. It is trying to drive the particles apart. But once you get them close enough together, it is the residual strong force that kicks in. You may just know this as the strong force, but the strong force is what happens between quarks. What happens between nucleons is a residual effect that gets channeled through particles called pions. So it is a different story there. But the point here is, once you get the atoms close enough, there is another force that takes over, and it sticks them together ferociously. And just like what happened with these two magnets, releasing energy through a loud noise, once two atoms fuse together this way, they also release energy. And just try to see that in the graph. So here, the force is repulsive, right? The more you push, the more it pushes against you. But over here, it is attractive. So now it is attracting the particles together. So now you're falling down here. Here you were giving energy to climb up. Here you're falling into a well. So the particles are going to release energy. This is the last piece of the puzzle. The star starts to fuse hydrogen into helium. Then what happens is the star becomes even more like an onion, because now in the core you start to get helium atoms, which are of course denser than the hydrogen atoms, and the hydrogen starts to clump up around the helium. So now we have layers in the core, and then it's hydrogen up to the surface. So that is the end of our story for now. If you have liked this video on stellar formation, be sure to subscribe and stay tuned for the next parts on how stars evolve.